Welcome to the deep dive. Today we're looking at a problem you've probably wondered about at some point. Like, as artificial intelligence gets smarter, how do we keep training it when it literally runs out of human knowledge to learn from?
Right, yeah. It's a massive issue.
Just, when we picture how AI learns complex reasoning, things like advanced math or software coding or graduate level physics, we usually imagine this endless, insatiable machine just devouring the entire internet.
Yeah, exactly.
We picture it reading like every Wikipedia page, every textbook, every forum post ever written.
And, I mean, for a long time, that brute force approach actually worked.
Right.
But we've reached a point where the internet simply doesn't have enough high-quality, verified, really complex logic puzzles to keep pushing these models forward.
It's like a student preparing for the hardest exam of their life. To get from a B+ to an A+, that student doesn't just need to read more general textbooks.
No, they need practice.
Exactly. They need masterfully crafted, incredibly difficult practice tests with, verifiable, logically perfect solutions.
Right.
But the problem we are facing right now in the AI industry is that human annotation, like having real-world domain experts sit down and write these elite practice tests, is just way too expensive and painfully slow.
It is genuinely the defining bottleneck of current generative AI.
Yeah.
Like, we've scaled the compute. Right? We scaled the parameters. We have massive server farms just humming away.
But you can't just scrape the web for it.
Exactly. You cannot scrape the web for the volume of elite reasoning data required to push these models to the next frontier. The data just, well, it doesn't exist out there in the wild.
Which means basically the AI has to learn how to teach itself.
Precisely.
So to figure out how we get AI to do that, our mission today is to explore a cutting-edge, state-of-the-art paper that is completely shaking up the foundations of how we approach this.
Yeah, it's a brilliant piece of research.
The paper is titled Agentic Proposing, Enhancing Large Language Model Reasoning via Compositional Skill Synthesis.
Quite a mouthful.
Yeah, definitely. It comes from researchers at Alibaba Group, Shanghai Jiaotong University, Shanghai University of Finance and Economics, and Wuhan University.
Right.
And they've essentially built an AI agent that acts like a master exam writer. It autonomously generates its own insanely difficult, logically perfect practice problems to train other models.
And it isn't just like generating text. It is actively engineering the logic behind the problems.
Oh, wow. Okay.
Yeah. And to understand why this is such a massive leap, we kind of have to look at the wall the industry just hit with traditional data synthesis.
Right. The current paradigm. Because we are already generating data synthetically, right?
We are, yeah.
Yeah.
We currently use methods covered in the paper like metamath or wizard math.
Mm-hmm.
And those basically take an existing seed problem, like a math question we already have, and try to evolve it.
So they just rewrite it.
Exactly. They might swap out variables or, add a slight complication. Or you have other methods like MathSmith and ScaleQuest that extract concepts from structured knowledge bases and try to recombine them.
But those methods rely on a safety net, right?
Yeah, big time.
Okay, let's unpack this. They use what the researchers call generation templates, or fixed structural priors.
Right. And it leads to this massive recurring problem in the industry, this trade-off trap.
A trade-off between what?
Between validity and difficulty. So if you want to guarantee that the math problem the AI spits out is actually solvable like structurally valid, you have to force the AI to use a rigid, human-designed template.
But if you force it to use a template, you cap the difficulty.
Exactly. The AI can never generate something truly novel or mind-bendingly hard because it's forced to stay on the rails we built for it.
It's basically the difference between playing Mad Libs and writing an original mystery novel.
I love that analogy, yeah.
Right, because with Mad Libs, you have this rigid template. You ask for a noun, a verb, an adjective, and the final sentence is absolutely guaranteed to be grammatically correct.
Right, it's structurally valid every single time.
But it's totally safe. It's not complex. Now, if you tell a standard AI, hey, throw away the Mad Libs template and just go write a highly complex original mystery novel, meaning you relax those constraints to try and make the problem harder.
The internal logic almost always collapses.
Yeah, the AI just generates totally unsolvable gibberish. Like, it might accidentally make the butler the killer in Chapter 1, but then, explicitly state the butler was the victim in Chapter 3.
Exactly, because open-loop, single-pass text generation is incredibly unstable when you dial up the difficulty. The AI is fundamentally just predicting the next word. It isn't verifying the underlying logic of the whole structure as it goes.
So it just kind of rambles itself into a logical corner.
Yeah, pretty much.
Yeah.
So the big shift here, the core thesis of this paper, is that synthesizing high-difficulty problems shouldn't be treated as a monolithic text generation task at all.
Okay. You can't just prompt an AI and say, hey, write a hard math problem. It needs to be treated as a process of compositional logic engineering. Compositional logic engineering. Okay, so how do they actually break that down? Because getting away from the Mad Libs problem sounds really hard.
It is, but what they did is introduce this concept of composable agent skills.
Composable agent skills.
Yeah. Instead of asking the AI to spit out a full problem in one go, the logic is broken down into atomic modular reasoning components.
So tiny little blocks of logic.
Exactly. And I'm going to geek out a bit on the details here, but each atomic skill is formalized as this very specific attribute tuple containing 4 distinct things.
Okay, lay it on me.
First, the reasoning intent, like what specific logical leap are we trying to achieve? Second, the construction method. How do we actually build it?
Got it.
Third is the difficulty effect, meaning how much harder will adding this specific thing make the final problem? And fourth, a tool use hint.
A tool use hint, like what?
Like what external tools might be needed to verify this step. So it's not just a vague text prompt. It is a discrete executable component of logic.
So to make this tangible for you listening, it's really like building with Lego bricks.
Yeah, that's a perfect way to put it.
Because traditional data synthesis is like handing the AI a single molded plastic toy, right? Like a toy car. It is what it is. You can't change its fundamental shape.
Right, the rigid template.
But with this autonomous skill library, the AI gets a massive box of individual Lego logic bricks. It can dynamically select and snap these bricks together to create completely novel, high-difficulty problems.
What's fascinating here is that the agent doesn't just combine these Lego bricks blindly. It actually models the synthesis as a goal-driven sequential decision process.
Okay, what does that mean in plain English?
Specifically, a partially observable Markov decision process, or POMDP.
Wait, partially observable, meaning it can't see the whole thing.
Exactly, because the logical solvability of a problem is a latent or hidden property.
Oh, I see.
The AI has to actively probe its environment to know if the problem actually works. Just snapping the bricks together doesn't mean the bridge won't collapse.
Right, like building a bridge in the dark. You can snap the steel beams together based on blueprints. You know what each beam does, but you don't actually know if the entire bridge will hold weight until you run a truck over it.
Exactly. So to reduce that uncertainty, it uses a closed-loop workflow.
And that loop is draft, check, refine, and finalize.
Yep. It's constantly acting as its own editor. And it uses specific actions to do this. For example, it uses an action called tau-think.
Tau-think, like an internal reflection.
Exactly. It generates private reasoning chains to audit its own logic before it outputs any observable text. And it pairs that with interactive tools, like tau-exec.
Which does what?
tau-exec lets it run sandboxed code to actually mathematically verify its own work.
Okay, wait, I gotta push back slightly here. Isn't this just a very fancy prompt telling the AI to think step by step? I mean, we've seen that a million times.
It sounds similar, but there's a massive difference. And that difference is dynamic skill pruning.
Pruning, like cutting things away.
Exactly. They introduced this highly advanced action called tau-edit.
Okay.
So usually, if a traditional AI realizes it made a logical error mid-sentence, it just hallucinates a fix, right? It tries to justify a flawed premise, and the whole thing unravels.
Yeah, it just doubles down on being wrong.
Right. But with tau-edit, if the agent realizes mid-draft that a specific Lego brick it chose is misaligned and causing errors, it doesn't hallucinate. It proactively reaches in, prunes that skill from its active set, and tries a completely different path.
Wait, really?
Yeah.
It literally deletes its own bad idea from its cognitive context in real time.
Yes. It catches the flaw and pivots.
That is wild, and there is a staggering stat from the paper's ablation studies that proves this.
The validity jump.
Yeah, so when they turn off this dynamic pruning ability just to see what would happen, the validity of the generated problems, meaning they were actually solvable, sat at about 68.7%. But when they gave the agent its pruning ability back, that validity shot up to 82.3%. It's literally catching and fixing its own bad ideas.
A jump like that is huge. It proves agentic correction is completely indispensable here.
Okay, but how do they even train a model to behave this way? You can't just hand an AI a box of logic bricks and be like, good luck, have fun.
No, definitely not. They built a 3-stage training pipeline. Stage 1 is basically extracting these atomic skills from large corporate textbooks, papers, stuff like that, to build the library.
It makes sense.
Then stage 2 is Agentic Supervised Fine-Tuning. or SFT. That's where the agent learns by mimicking expert trajectories.
But those trajectories have to be flawless, right?
Oh yeah, they are rigorously filtered by a massive three-model verifier ensemble.
Like a Supreme Court of AI judges.
Exactly. And it includes heavyweights like GPT-120B and DeepSeek v3.2 Special. They don't mess around with the filtering.
Okay, so that gets us a really solid foundation. But here's where it gets really interesting. Because stage 3 is something called Multi-Granularity Policy Optimization, or MGPO.
Yeah, MGPO is the secret sauce here.
Why? What's wrong with standard reinforcement learning?
Well, standard RL, like GRPO, actually fails miserably here.
Yeah.
When these baseline models get too smart, their pass rates on standard tests get incredibly high, like 85 to 89%.
Which sounds good, right?
It sounds good, but it causes something called entropy collapse.
Entropy collapse.
Yeah. Basically, the reward signal completely vanishes because almost every attempt the model makes gets a positive reward.
Oh, I see. It's like a dog on an agility course.
Okay, let's hear it.
Standard DRPO is like a teacher or a trainer who only gives the dog a treat if it crosses the finish line perfectly.
Right.
But if the dog is already elite and clears the course 90% of the time, handing it a treat at the end doesn't teach it how to get faster on the seesaw, right?
Yeah.
It just reinforces what it already knows.
That is exactly it. If you only grade the final answer on a math test, the student can't improve their underlying process. MGPO, however, grades the entire process.
So it grades the micro behaviors.
Precisely. MGPO standardizes rewards at two different granularities. First, you have the global trajectory level advantage.
Which is the finish line treat. Did the final question make sense?
Yep. But then you have the local stage level advantage. Did the agent use the code tool correctly? Did its internal reflection make sense? Did it successfully prune a bad skill?
So it gives a tiny reward for clearing the first jump, balancing on the beam, and penalizes taking the wrong tunnel.
Exactly. And this multi-granularity approach resulted in a massive plus 6.5-point absolute improvement over standard GRPO.
Wow. So it forces the model to actually explore high-difficulty compositions.
Right, instead of just playing it safe to get the final answer treat.
Okay, so we've got this amazing agentic proposer. It drafts, it audits itself, it prunes bad ideas, and it's trained on this super dense MGPO grading system.
Yep.
But the real question is, what happens when you take this pristine, self-generated practice data and use it to train a downstream AI solver?
The results are pretty jaw-dropping, honestly. They started by testing a small 4 billion parameter solver.
4 billion parameters is tiny.
Very tiny. And they trained it on just 10,000 synthesized trajectories.
Which, again, in an industry that uses trillions of tokens, 10,000 is basically nothing.
It's microscopic. But that 4B model significantly outperformed established baselines on contest math.
That's crazy. But the biggest mic drop of the paper, like the real David versus Goliath moment, is when they scaled up to a 30 billion parameter solver.
Oh, the 30B results are unbelievable.
Well, right. They trained this 30B model on only 11,000 synthesized trajectories. And on the incredibly difficult AIM 2025 math benchmark, this model achieved a state-of-the-art 91.6% accuracy.
Yeah, and if we connect this to the bigger picture,
Yeah.
91.6% means this 30 billion parameter model completely outperformed open source models with up to 20 times more parameters.
Wait, 20 times?
Yeah, we're talking about beating giants like Mistral 3, which is 675 billion parameters, and DeepSeek v3.1, which is 685 billion.
That is absurd.
It totally surpassed Grok 4.1 Fast and Claude 4.5 Opus,
Yeah.
and it rivaled frontier proprietary models like GPT-5 and Gemini 3 Pro.
A 30B model doing that just because the practice problems it learned from were so incredibly dense and perfect.
Exactly.
And it's important to note, this isn't just a math trick.
Wait.
Like it didn't just memorize some formula.
No, not at all. The framework showed incredible transferability to coding, like on the live code bench, and even graduate-level science reasoning on Super GPQA.
So it's developing true cognitive robustness.
Yeah, it's not just memorized domain tricks. It's actually getting smarter.
Okay, we've covered so much ground here. We've gone from the limitations of those rigid Mad Lib-style templates to an autonomous, self-correcting agent that builds complex puzzles out of Lego logic bricks.
Right.
And ultimately, it's training tiny models to punch way, way above their weight class. So what does this all mean?
Well, it means the true bottleneck for super advanced reasoning isn't having trillions of parameters, and it's not infinitely scaling up data quantity.
It's quality over quantity.
Exactly. The bottleneck is the density of high-quality training signals. This paper proves that a very small volume of perfect agent-synthesized data can totally substitute for massive, noisy data sets.
It's a total paradigm shift, and it really leaves you with a profound thought to mull over.
Yeah.
If a relatively small AI can act as this expert curriculum designer-like, autonomously generating the exact perfect puzzles needed to train the next generation of AI to beat human benchmarks.
What happens when we just let it run?
Exactly. What happens when we unleash this capability continuously? Will the path to artificial general intelligence rely less on scraping the internet for human knowledge and more on AI models just sitting in a virtual room, endlessly crafting and solving their own master-level logic puzzles?
It's totally possible. The self-improving loop is right there.
It's wild to think about. But that's all the time we have for today. Thanks for joining us on this deep dive. Keep exploring, and we'll see you next time.